Welcome to Math with Professor V. In this video, I'm going to work through and solve the most recent exam that my Precalculus class took. So it covers a lot to do with polynomial functions, rational functions, exponential functions, logarithmic functions, solving equations, really good stuff. So even if you're in calc, this would be a good review of topics and things that you're going to still be encountering for the rest of your math career. So first question, solve the inequality and then write your final answer in interval notation. So when we have a higher order inequality, remember there's a different process than the way you solve equations. So we do first need to factor the left-hand side completely. So I'm going to start off taking out an x, and then I have x squared plus 3x minus 18 is greater than 0. I have to keep factoring. So what two numbers multiply to negative 18 but add to 3? Can you think of them? Good. It's positive 6 and negative 3. Now from here, this is where things are different. If it was an equal sign, I would use the zero product property, right? And then pretty much be done in a step or two. But this is an inequality. We deal with them differently. So I'm going to list all of the zeros from the factors on a number line. So what are the zeros? 0, negative 6, and positive 3. Those go on a number line, and you don't have to worry too much about scaling, just place them in the appropriate order. So, negative 6 is here, then 0, then 3. I know it's not to scale, it's all good. And this has broken up the real number line into 4 different intervals. 1, 2, 3, 4. I like to list them out before I get started solving the problem. So this first one goes from negative infinity up until negative 6. And I'm going to put parentheses instead of a bracket because notice this inequality is strict. It says greater than 0. So if you have something that's greater than or less than, that's when you use parentheses. If you have greater than or equal to or less than or equal to, that's when you use a bracket. Good? Okay, next interval goes from negative 6 to 0. Next one from 0 to 3. And then lastly, 3 to infinity. Very good. So those are the 4 intervals. Now what you're going to do is you pick a value from each of these intervals, some representative value, and you test it in the left-hand side of the inequality to see if it gives you a true statement, if it satisfies the inequality. So for example, pick a number between negative infinity and negative 6, and don't ever pick the endpoint, okay? So shall we test with negative 7? Yes, you could do negative 42, negative 100, any of those will work. You can plug them in anywhere, but the easiest place is into the factored version. And all I want to see is if x equals negative 7, we'll make the left-hand side greater than 0. In fact, I don't even care what number I get. I just want to see if it's positive or negative. So this is the fun part to me. If I plug in negative 7 for x, that's going to be negative. If I plug in negative 7 for x into x plus 6, negative 7 plus 6 is negative. And then negative 7 minus 3, that's also negative. Notice I'm not worried about what numbers I'm getting, I'm just keeping track of the signs. So if I have a negative times a negative times a negative, the outcome's going to be negative. Remember, when you have 2 negatives, those make a positive. But if you have an odd number total, then everything's going to stay negative. So that means anything from this interval, from negative infinity to negative 6, will make the left-hand side of the inequality negative. Well, is that what I want? Would that satisfy the inequality? The inequality says it wants the left-hand side to be greater than 0, meaning positive, not negative. So nothing, sadly, from this interval will satisfy the inequality. You only have to test one value, and it'll tell you what's going to happen for everybody else in that interval. Okay? Good. Let's repeat the process now. So from negative 6 to 0, what do you want to test with? You could do negative 5. You could do negative 1. Let's do negative 1. And again, I'm coming back right here, and I'm testing the sign of each of the factors. So this would stay negative, right? Negative 1. Negative 1 plus 6, this would be positive. And then what about negative 1 minus 3 right here? Then that factor is negative. So a negative times a positive times a negative, overall that's going to give me something positive, right? Because these two negatives will cancel and make a positive. Well, does that work for us? Yes, because if this is positive, that's greater than 0, that satisfies the inequality. So that works. That's going to be part of our solution set. Now from 0 to 3, I'm going to test with x equals 1. I'm going to go more quickly now. So we'll have positive, positive, negative. Everything's going to be negative. Nope, that does not work for us. So sorry. And then from 3 to infinity, we can test with 4. So that would be positive, positive, positive. Everything's positive. Yep, that works. So when you write your final answer, the direction said to give it an interval notation, and we're just going to join them together, meaning you go from -6 to 0, because if you'll recall, this interval worked. Yes. And then put union, or you could write the word or, up to you, 3 to infinity. And that's it. Okay, good. I'm going to link all the video lectures that cover the topics in this exam, just in case you need a refresher, because I'm just solving the problems. I'm explaining a little bit, but not like super in depth. So if you need more explanation, I'll link everything in the description. Okay, the next one is rational inequality. So very similar process. You do also still list the zeros from the numerator as well as the denominator on the number line. So we got to get to factoring. 2x squared minus 5x minus 7. So a lot of students struggle with factoring. I have factoring review videos if that applies to you. You're not alone. I don't do anything fancy, really. I just do guess and check methods. So 2x squared, I think to myself, what are my options to get 2x squared for the first term? There's only one set of options, 2x and x. That's pretty good. What about 7? Again, the only way you get 7 is 1 times 7. Now I notice it's negative, so one of them is going to be positive, one of them is going to be negative, and I want the middle term to be 5. So then at this point I'm already imagining, I don't want the 7 right here. Nope. How do I know that? Because then 2x times 7 would give me 14x, and I'm trying to get 5x happening. So feeling like the 1's going to go here, the 7's going to go here, yes? This is 2x, this is 7x. I want negative 5x altogether. So this 7x needs to be negative, and then this is positive, and we're done, okay? Good, so let's list the zeros from the numerator as well as the denominator on the number line, just like we did in the last problem. We do have to be a little careful though, because we're gonna have to include some domain restrictions. So from the numerator, 2x minus 7 means x equals 7 halves is a 0. 7 halves, 3.5. Also x equals -1 and x equals -2. Now, I know -2 is a 0 from the denominator, so it is a restriction. We can't include -2 in our solution set, but it still is important to list that 0 on the number line because the sign of the expression could change on either side, okay? So don't neglect it. You don't get to multiply through and clear denominators out in inequalities the way you would if it was an equation. So like you're not losing your mind. If you had some, oh, why is this so chunky? Oh, no. I just want you to, if your instinct was to clear it out, that's because you're thinking of an equation. So when you have something like this and there's an equal sign, yeah, go for it. Multiply everybody by x plus 2, right? And then you just have 2x squared minus 5x minus 7 equals 0. And all is well. But in an inequality, you're not allowed to do that, unfortunately. So they just take more care. I just think of inequalities as high maintenance, you know? We can't do the things we do with equations. Okay, so let's again list out our intervals. This time, did you notice the inequality is different? It's inclusive, less than or equal to 0. So I'm going to use brackets for the endpoints. The only endpoints that wouldn't get brackets are infinities, right? You always put parentheses on infinities, as well as -2, because that is a domain restriction. So this is going to be a little interesting. First interval goes from -infinity to -2, parentheses on -2 because it's a restriction. And then we're going to go -2 to -1. -1 gets a bracket because -1 is a 0 from the numerator. So we can include it in our solution set since the inequality is inclusive. And then the next one is going to go from -1 to 7/2. Put brackets on those. And then lastly, 7/2 to infinity. Always parentheses on infinity. Okay? Good. And then same process as the last problem. So you're going to pick a representative value, say -3. And I'm going to substitute that into each of the factors to see what the sign is of the expression on the left. All right? So -3 times 2, that's -6, minus 7, that's negative. -3 plus 1, that's negative. Divided by -3 plus 2, that's negative. So just count up. If I have an odd number of negatives, then everything's going to stay negative. You need to be able to pair them up for them to cancel and make something positive. So, nope, everything here is negative. Why did I say no? That's what we want, right? So this time the inequality says less than or equal to 0, which means we want the left-hand side to be negative. So yay, that works. That's what we're going for. Okay, from -2 to -1. You still have to pick something between. You can't pick -1 even though there's a bracket because it's just going to give you 0. It won't tell you if it's positive or negative. So between those two values, let's test with x equals -1.5. Okay, so 2 times -1.5, that's -3. Minus 7, that's negative. -1.5 plus 1 is negative. -1.5 plus 2 is positive. So 2 negatives make a positive, divided by a positive, everything here's positive. Do we want that? This time, no. Remember, our inequality is less than or equal to 0, so we want something to be negative. Next interval, I could test with 0, right? Love it. So that'll be negative, positive, over a positive, so that's going to give me negative values. That works. And then anything from 7/2 to infinity. So 7/2 is 3.5. You can test with 4. So 2 times 4 minus 7, that's positive, positive, positive. Everything's positive. We don't want it. I mean, in general, it's good to be positive, but not for this problem. Okay, so the two intervals that worked were -infinity to -2. Union -1 to 7/2. And that's it. All right, very good. Moving on. For the following function, state the degree of the polynomial, determine its end behavior, find the x and y intercepts, determine whether the graph crosses or touches the x-axis at each x-intercept, and then draw a complete graph by hand. I gave a hint, be sure to completely factor first. So notice f of x here is x squared. X squared minus 9 factors into x plus 3 times x minus 3. And then we had another x plus 3. Do you see that? So I can combine these two factors of x plus 3 and just write it once as x plus 3 squared. So this is x squared, x plus 3 squared, and x minus 3. Okay, so what's the degree of the polynomial and its end behavior? Well, it's not all multiplied out, but if we were to multiply it out, the highest power on x would be 5, right? And you could see here, you could just kind of add up the exponents. 1, 2, 3, 4, 5. So it's a degree 5 polynomial. And the power function that it resembles for large values of x is y equals x to the 5th. If I sat there and multiplied it out, that would be the leading term. So x to the 5th is going to resemble the shape of x cubed. And the end behavior, all I need is for them to just draw me a little squiggle like that or just write y equals x to the 5th. Sometimes your teachers would want you to start working and practicing with limit notation. So you could write the limit as x goes to infinity of f of x. It approaches positive infinity because notice this side's going up. And then the limit as x goes to negative infinity of f of x, that's going to be negative infinity because the graph falls to the left. If you're not familiar with writing anything with limits, that's fine. And I don't make my students do it just yet. I just show them. That way they kind of start getting used to the idea of limits, since that's what you're going to study for a good chunk of Calc 1. Okay, next we're going to find the x and y intercepts of the graph. So the good thing is that it's totally factored for us. So you can just go through and set each of the factors equal to 0. So this lonely little x squared, if you set x squared equal to 0, you just get x is 0. X plus 3 squared equals 0 means you would get x equals negative 3. And then x minus 3 equaling 0 means x equals 3. But I make them write their intercepts as ordered pairs for one very important reason. And that reason is just leaving it as x equals, when in terms of graphing, is the equation of a vertical line. And intercepts are not lines, they're points, right? They're ordered pairs. So I recommend you always write your intercepts as ordered pairs. Don't leave it as x equals whatever. Those are the x-intercepts. Now what about the y-intercept? Well, to get the y-intercept, you substitute in 0 for x. F of 0, if I plug in 0 for x right here, this is going to give me 0 squared times 0 plus 3 squared times 0 minus 3. And 0 times anything is 0. 0 times any number is 0. So we already had it right here. Yeah? And you can have more than one x-intercept. A function can never have more than one y-intercept, because then it wouldn't be a function. It would violate the vertical line test. So we're good. We already got this, but we confirmed. Now what we want to do is figure out whether the graph is going to cross or just touch and like bounce back off the x-axis at each x-intercept. And the way to tell is by looking at the multiplicity of each of the intercepts. So 0, 0, that has multiplicity 2 because it came from x squared, right? So that root is in the polynomial twice. If the multiplicity is 2, an even number, then it touches the x-axis at that point. Negative 3, 0, what was the multiplicity of that root? That's multiplicity 2 also. This one's multiplicity 2 because of the exponent. The exponent, it tells you how many times it's there. So it touches here. And then lastly, what about at 3, 0? What's the multiplicity of that root? Well, there's just a 1 on the exponent. We don't write it, but the multiplicity is 1. So if the multiplicity is odd, then it crosses the x-axis at that intercept, okay? And then now we're going to draw a graph. So all they need to include are the intercepts and then just get the overall shape and the end behavior right. So we have 0, 0, 3, 0, negative 3, 0, and just remind yourself it's going to look like this, more or less. So what I do is I'm going to approach this first 0 from below because the shape should match here. And then as I approach negative 3, I know I'm not going to bounce up here because it's just supposed to touch the x-axis at that intercept. So I'm going to come up, up, up. Oh, sorry. It's so wiggly. Up, 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 and then turn around. And then I don't know how low we're going to go because I'm just doing this as a pre-calc student. When you're in calculus, you're going to figure out how low the graph goes, where it turns around, and then when it's going to come back up. But right now, in pre-calc, just live your best life and just draw it wherever your heart desires. Now, what should I do here at 0? Am I going to pop through or go back down? Check here. Oh, I'm just supposed to touch. So I'm going to turn around, come back down. How low do I go? Here or just to here? You don't know yet. When you're in calc, you'll find out. So just, enjoy the freedom. Turn it around when you're in the mood. And then here, what do we do at 3, 0? We cross through to the other side. Fabulous, fabulous. And don't forget arrows on the ends. And you're done. So overall, if you were to zoom out, this graph looks just like this. It just got extra wiggles in the middle, but if you zoom out far enough, you wouldn't see them. So we know we did things correctly. Okay? Beautiful. Now for a rational function. So state the domain and the x and y intercepts. I'm going to factor completely first. So the numerator factors into x plus 6, x minus 6, and the denominator into x plus 2, x minus 2. So the domain for a rational function is everything except what makes the denominator 0. So all x's such that x does not equal 2 and negative 2. Good. Now to get the x-intercepts, I really just need to look at where the numerator is equal to 0. So if we take x plus 6 and x minus 6, set them equal to 0, I'm going to get negative 6, 0, and 6, 0. Now the y-intercept takes a little more work. I would actually plug it into the original. It'll be easier. So f of 0 equals 0 squared minus 36 over 0 squared minus 4, and negative 36 divided by negative 4 is 9. So the y-intercept is at 0, 9. Okay, good. Give the equations of the vertical asymptotes, if any. Well, we didn't have anything cancel, so that means we don't have any holes in the graph. All of the zeros from the denominator are going to be vertical asymptotes. So that's going to be at x equals 2 and x equals negative 2. So you can see, this is why I don't like writing x-intercepts as just x equals. You need to put them as ordered pairs so that you know these are points and these are vertical lines. These are asymptotes. You see the differentiation? Okay. Give the equation of the horizontal or oblique asymptote. We have a horizontal asymptote. How do I know? The degree of the numerator is 2, and the degree of the denominator is 2. When the degrees are equal, you have a horizontal asymptote, and you get the equation for it by dividing the leading coefficients of the numerator over the denominator. So leading coefficient in the numerator is 1, leading coefficient in the denominator is 1. 1 divided by 1 is 1, so y equals 1. Okay, last thing before we graph, determine whether the graph crosses its horizontal or oblique asymptote. So the way to do this is I want to check if f of x is ever equal to the equation of its horizontal asymptote, which in this case is 1. So f of x is x squared minus 36 over x squared minus 4. Does that ever equal 1? I should put a question mark. So if I just multiply x squared minus 4 over x squared minus 36, does that ever equal x squared minus 4? You can cancel the x squareds out on both sides, and then you can see negative 36. No way, that doesn't equal negative 4. So that means no, the graph does not cross its horizontal asymptote. Okay? Good, and then now we're going to draw a complete graph by hand, label all the intercepts and asymptotes. So since we have to go out to 6, I'm going to scale by 2's in the x direction. So that's 2, 4, 6, negative 2, negative 4, negative 6. Okay, and then same thing here because the y-intercept is at 9, right? That's 8. So let's put 0, 9. 6, 0, negative 6, 0. Those were my intercepts, if you forgot, see? And then we'll put the vertical asymptotes in, plus or minus 2. And then we have a horizontal asymptote, y equals 1. And we're good. I actually know what the graph's going to look like. There's 3 parts, right? Because if there's 2 vertical asymptotes, then there's 1 part, 2 part, 3 parts. Over here, the graph has to be below the horizontal asymptote so that it can go through this x-intercept. Boom, beautiful. In the middle, now I don't know exactly, how low it's going to go or whatnot. I'm assuming it's got, this has symmetry with respect to the y-axis. So we should be good. You can just draw it like this. I know it won't do anything else. It can't come down. Why do I say that? Because then it would cross the horizontal asymptote and cross the x-axis. We found the only x-intercepts that there are. So, don't add new information that you didn't find prior to graphing. And then lastly, this little piece is just going to be down here. Okay, good. Yeah, if you remember testing with symmetry, I could show that f of negative x equals f of x if you go back to the original function. So we have symmetry with respect to the y-axis. So that's helpful. Then you know if you were to fold the graph on the y-axis, you should have a mirror image on both sides. Okay, good. We're going to take a little break from graphing now. I know. And a lot of students don't like graphing. You know, it's just because it's difficult. You need to really get good at it though, especially if you're going to keep going with calculus. So just keep practicing till it doesn't stress you out so much. Then it'll be fun. Then it's like art class almost. I don't know. Use the given 0 to find the remaining zeros. So because of the directions, I don't want them just guessing using the rational roots theorem. I want you to actually use this given 0 to definitively find the remaining ones. Ooh. So first we're going to use the conjugate pairs theorem. If 3 plus 2i is a 0 of this polynomial, so is 3 minus 2i. And I know there's going to be 4 total zeros because the degree of the polynomial is 4. So to get the remaining 2 zeros, right, I've already got 2 of them, I'm going to make a polynomial, namely a degree 2 polynomial that contains these 2 zeros, long divided into the original function, and the quotient will contain my missing zeros. You'll see. So here I'm going to form a polynomial with the zeros 3 plus 2i and 3 minus 2i. So I do that by writing the factors x minus each of the zeros. And then to multiply it out, watch this. First I'm going to distribute the negative. So then I have x minus 3 minus 2i and x minus 3 plus 2i. Don't just sit there foiling right now. Too many terms, it'll stress you out. What I want you to do is group x minus 3 and observe that basically you have y minus 2i times y plus 2i. Those are conjugate pairs, right? It would just multiply out to y squared minus 4i squared, and that's exactly what you have here. Just think of x minus 3 as y. Group them together. So then I could write this as x minus 3 squared minus 4i squared. And it saves you the headache of all that foiling. If you've never seen this before and you want to practice more examples, then go to the video lecture on this section because I do plenty. Okay, x minus 3 squared, that's x squared minus 6x plus 9 minus 4 times I squared is negative 1. Very good. So this is going to give me x squared minus 6x plus 13. So these 2 zeros are in this polynomial. Like if you were to do quadratic formula all over again, you'd get back 3 plus or minus 2i. I'm going to divide this into f of x. And the quotient, what I get after dividing, will contain the missing 2 zeros. So let's hop to it. I'm going to divide as if you remember how. If you don't, it's all good. I got a video reminding you how to do polynomial long division. Because unless you do math on the daily, I don't think it's something you're going to remember. 2x to the 4th minus 17x cubed plus 58x squared minus 77x plus 26. Okay, so you just start off always looking at the leading terms only. So what do I multiply x squared by to make it 2x to the 4th? 2x squared. And then that distributes, and I'm going to list the result underneath. So 2x to the 4th minus 12x cubed plus 26x squared. And then subtract this row from the row above. The terms on the far left should always cancel. And then just be careful with that negative. So negative 17 minus negative 12 is negative 5x cubed. And then 58 minus 26, that's going to be plus 32x squared. And then I'm going to bring down the next term, negative 77x. And then just repeat. So you look again just at x squared. What do I multiply it by to make it negative 5x cubed? Negative 5x. Then I distribute that. So negative 5x cubed plus 30x squared. I'm distributing it to the divisor, everybody out here. 5 times 13, so minus 65x. And then we subtract this from the row above. So these cancel. 32 minus 30 is 2x squared. Negative 77 plus 65, negative 12x. And then bring down the last term, 26. Okay, we're almost done. X squared, what do I multiply it by to make it 2x squared? Just plus 2. And then this is 2x squared minus 12x plus 26. You should have no remainder because you divided by a polynomial containing two of the zeros of this polynomial. If you get a remainder, you messed up, okay? Now, my remaining two zeros are sitting right in here. So I just need to solve 2x squared minus 5x plus 2 equals 0. And it factors 2x, x. 2 is going to be 2 times 1. They should both be negative since the middle term's negative. And then you get x equals 1/2 or x equals 2. So let's go back, answer the question. 1/2, 2, and 3 minus 2i. So find the remaining zeros. So the remaining, they gave me 1. The remaining ones are 3 minus 2i, 1/2, and 2. But if you wanted to write like all the zeros, a complete solution set, it's 3 plus or minus 2i, 1/2, and 2. And they didn't get full credit if they just sat there using the rational roots theorem and just guessed and checked and did synthetic division until they got 1/2 and 2, because the direction said that you needed to use the given 0 to find the remaining ones. So the remaining ones were found via polynomial long division. Okay, good. Next, very important idea, especially if you're going to go on to calc, is domain of composition of function. So find the domain of the composite function f composed with g. So first thing you have to do is find that composition. So f composed with g means f of g of x. I'm going to plug in or substitute g of x everywhere I see x in f. So in the numerator, instead of x, I'm going to put 16 over x plus 5. And then the denominator, same thing, 16 over x plus 5, and then plus 4. Now from here, we got to simplify, right? It's a complex fraction. So easiest way to do it is just multiply top and bottom by the LCD, or the denominator that you're trying to get rid of, which is x plus 5. So see, like now this will cancel. And I just have 16 up top. And then in the denominator, if you distribute, this x plus 5 will cancel. So I'll just have 16 plus, it doesn't cancel though with the 4, right? So you're still going to have 4 and then put parentheses x plus 5. We're going to multiply that out. So now we have 16 over 16 plus 4x plus 20. So that's 16 over 4x plus 36, right? And I can take a 4 out. So that's 4 times x plus 9. Cancel that with the 16 in the top, and we have 4 over x plus 9. So now I have to find the domain of this new function, this composition function, and it can be a little tricky. So right off the bat, I go, okay, it's a rational function. I know the denominator can't be 0, so I have to say x cannot be negative 9. But then also I have to include any restrictions that there are for that inside function g of x that maybe we don't see anymore. And if you look back at g of x, it does have a restriction. X can't be negative 5. And that was apparent at this initial step. But when we clear out the denominators and multiply by x plus 5, now you can't see it anymore. You can't see the problem, right? Especially once we've cleaned up. So just be on high alert with compositions. You always have to include the restrictions from the inside function as well as the final function. So x can't equal negative 5 either. Even though, right, looking here, you might have forgotten about the negative 5. Negative 4 is not a problem, okay? The restrictions for the outside function don't come into play if you don't see them at the end. It's only the ones for the inside function that are relevant, okay? Good? I know, these ones take practice. They're rough, so I have plenty more if you want to go to the video lecture and practice. One more, f of x equals 4 over x minus 5, and g of x is rad x minus 4. So same thing, we're going to first find the composition, f composed with g of x. So f of x is 4 over, instead of x, I'm going to write rad x minus 4 minus 5. Excuse me. So, I mean, you can stop here. Some students, oh my goodness, they impressed me. They rationalized that denominator. They multiplied by the conjugate. I'm cool. Just leave it here because it's easier to find the domain with it like this. Two things to consider, okay? Restrictions for g of x. So let's look at g of x really quickly. It's rad x minus 4. Well, what do we know about radical functions that have an even index? Even index means it's a square root or a fourth root or a sixth root. Well, you can't take an even root of a negative number and get a real number. So whatever's underneath the radical, we call that the radicand. You don't need to know the name unless you're going to explain it to somebody else. Okay, just the stuff underneath the square root sign, it can't be negative. So x minus 4, that's the stuff under the square root. How do we say something can't be negative in math? We say it has to be greater than or equal to 0. And then just solve that inequality. That's going to give you the domain for that part of the function. X has to be greater than or equal to 4. Okay? So that's g of x's domain. I have to include that because that's the inside function in the composition. Now, look at this final function here. It's a rational function. So I know the denominator also can't be 0. So rad x minus 4 minus 5 can't be 0, which means rad x minus 4 can't be 5. Square both sides, x minus 4, it better not be 25. Don't push me, x better not be 29, okay? So is that relevant to list? Yeah, x has to be greater than or equal to 4. 29 is greater than 4, so we got to make sure we tell everybody skip over 29. It's a no-no. It will make the denominator 0, making the whole function undefined. So the domain is all x's, such that x has to be greater than or equal to 4 and x is not equal to 29. Some people wrote this in interval notation. That's cool. You would go 4 to 29, union 29 to infinity. Whatever, I didn't care. I didn't say in the directions. I think set builder's easier for these, but you do you. Okay. How's everyone doing? Good. Find the inverse function of f, state the domain and range of f and its inverse function. So whenever you find the equation for the inverse of a function, you're going to go ahead, start off, let me replace f of x with y. And then now I'm going to interchange my variables. So you swap all your x's and y's, meaning I'm going to write x equals 2y plus 7 over y minus 5. Are we good? Perfect. Now my goal is to solve for the new y. So I'm going to multiply both sides by y minus 5. So x times y minus 5 equals 2y plus 7. We need to distribute. And then since I'm trying to solve for y, I need to get all the terms that have y on the same side of the equation. So let me move this 2y over to the other side, okay? So I have xy minus 2y. And then everything that doesn't have a y needs to go on the same side. So 5x plus 7, they need to hang out there. When I explain it, I usually say everybody that has the variable that you want goes to the left, and then the rest, they get exiled to the other side. Okay, very nice. What's the point of that? So we can factor the y out on the left-hand side. So we have y times x minus 2 equals 5x plus 7. And then we're almost there. I can divide both sides by x minus 2, and I get y all by itself. But remember, the problem asked us to find the inverse of f. So we have to use correct notation at the end. Replace y with f inverse of x equals 5x plus 7 over x minus 2. Okay? Very good. So that's the first part. Then we're asked to state the domain and range of f and its inverse. So right off the bat, you should be able to figure out what's the domain of f. The domain of f is all x's such that x cannot equal 5, right? That would make the denominator 0. And looking down here at f inverse, can you tell me the domain? Good, all x's such that x can't equal 2. Now, how do you find the range? By looking at the inverse function. So the range of f is all y's such that y can't equal 2. Where did I get 2? Because it's the domain of the inverse. And then the range of f inverse is going to be all y's such that y can't equal 5. So the domain and range for a function and its inverse are always interchanged. Do you see that? And that should make sense, because if the domain is all possible x's in a function and the range is all y's, and the very first thing I did when I found the equation of the inverse was swap the x's and y's, doesn't it make sense the domain and range should swap? Yes, it makes sense to me. I hope it makes sense to you. So that's all you do. You get the domain of each, right, just by looking at the denominators. And then to get the range, you just swap them from the domain of the other. Okay? That's it. That was it. Number 7, solve the equation. Express irrational answers in exact form and as a decimal rounded to 3 decimal places. So we have here 2/7 raised to the x equals 9 raised to the 1 minus x. So in this case, there's absolutely no way I can express both sides of the equation in terms of the same base, right? 2/7 and 9, no way. So what you do is you take the natural log of both sides. Why would you do that? Because now you can move these exponents in the front using our log properties. So then now I have x times ln 2/7 equals 1 minus x times ln of 9. And ln of 9 is just a number, so distribute it through. X times ln 2/7 equals ln of 9 minus x times ln of 9. And this is so similar to the previous problem with the inverse because we're trying to solve for x. I have an x here and an x here. So they need to be on the same side of the equation so I can do that same factoring maneuver. So x ln 2/7 plus x ln 9 equals ln 9. We factor the x out, and then you have ln 2/7 plus ln of 9. If you want, you can combine these two using your log properties, make it ln of 18/7, but I didn't require that. Some students did it though, okay? It does make it easier to punch into your calculator at the end. So the problem asks for the, exact answer, which is going to be this one right here, all in terms of natural log. You also could have used common log on both sides, okay? This is the exact answer. ln of 9 divided by ln of 2/7 plus ln of 9, which you could rewrite as ln of 9 over ln of 18/7, if you want, okay? And this is approximately 2.326 if you punch it in your calculator. And the directions were specific, and they said to round to 3 decimal places. So make sure you follow directions. Yes. 3. Okay. Usually we don't do sig figs in math like we do in science. So typically they'll tell you how many decimal places to round to in the directions. Maybe some math teachers like sig figs, but usually we just are straight up about it. Okay, good. There's 10 questions, so we're almost at the end. Use transformations to graph the function. So f of x is -2 x raised to the x plus 1, so this is exponential function, plus 3. So state the parent function, original key points, and list the transformations in order. So the parent function is y equals 2 to the x. Not -2 to the x. The base is never negative. If you see a minus sign, then that's a reflection. That's part of your transformations. And the original key points on an exponential function that I have them use are 0, 1, 1 comma a. A is the base. So 1 comma 2, and then -1, 1/2. Now the transformations, I see 3 of them. The first one we have to deal with is the reflection, the minus sign outside. And since it's in front of the base and it's not touching x in the exponent, it's a reflection over the x-axis. So the way I'm going to make that happen is multiply all the y coordinates by -1. And then the x plus 1, that plus 1 means we shift left 1. So we're going to subtract 1 from all the x's to do that. And the plus 3 means we shift up 3. So we're going to add 3 to all the y values. Okay, so now we're going to give the final key points. Let me do the first transformation by itself. So I'm going to multiply all the y values by -1. So they'll become -1, -2, -1/2. And then now I'll take care of the last two transformations at the same time. So we can subtract 1 from x. It'll be -1, 0, -2. And then add 3 to the y value. So this will be 2, 1. -1/2 plus 3 is 2.5 or 5/2. Okay, so those are the final key points that we're going to graph. And then we also need to give the equation of the asymptote. So originally, the horizontal asymptote on an exponential function is at y equals 0. If we shift up or down, it will move. And since we shifted up 3 units, the new horizontal asymptote is at y equals 3. So put that on the graph first, honestly, y equals 3. It'll keep you honest. It'll keep you from going wild and fancy free. And then -1, 2, 0, 1, -2, 2.5 is here. And then just remember, exponential functions only have a horizontal asymptote. They do not have a vertical asymptote. So make sure it shows that it keeps going. You know, it's not like a rational function. It's not. That's it. State the domain and range. So use the graph, it helps. Domain, all real numbers, right? So -∞ to infinity. You could write all real numbers, I don't care. And then the range, the graph goes down, down, down forever. So it's going to go from -∞ up until 3 with parentheses, because it's never going to actually hit 3, right? The horizontal asymptote, it just gets super close, but it never hits it. My high school teacher would say, it's MC Hammer. Can't touch this. No. Do you even know that song? You guys are probably too young. Okay. Look, I still remember from more than 20 years ago. He was such a good teacher. Okay, that's that. Solving equations. I have one log equation, one exponential equation. So part A, we have log base 3 of x plus log base 3 x minus 24 equals 4. To start off, I want to combine these logarithms into a single logarithm. So we do that using our log properties. I can multiply the arguments. So remember, if you have log base b of x plus log base b of y, that's log base b of x times y. Okay, so I can write this as log, you have to write base 3, x times x minus 24 is x squared minus 24x. Good. Now we're going to rewrite this in exponential form. So this is equivalent to 3 to the 4th equals x squared minus 24x. You can do the loop-de-swoop. The loop-de-swoop. So you do 3 raised to the 4th equals x squared minus 24x. How do you solve? Don't even think about factoring unless there's a 0 on one side, okay? I don't want to see it. I don't want to hear about it. Scoot everybody over. First, x squared minus 24x minus 3 to the 4th is 81. Very good. Does that factor? Of course. I wouldn't be so cruel. X minus 27, x plus 3. So we get x is 27 or x is -3. But you got to be on high alert in math. You always have to maintain a healthy level of paranoia that there's some minor detail you've overlooked. And with log equations, remember, we have restrictions on domains of logarithms. Whatever the argument is, the stuff that I've highlighted, It has to be positive. So let's check. 27. 27, that's good. 27 minus 24, we're good. Negative 3, okay. What does that mean for poor negative 3? It's the end of the road for you. You don't get to go in the solution set. Only 27 is our answer. Okay, good. Next, we have an exponential equation. Unlike the one we did, which question number was it? Unlike number 7, I can write both sides in terms of the same base. So we don't have to bust out a logarithm to solve this. 9 to the 2x, I can write that as 3 squared to the 2x. 27 is 3 cubed to the 3 minus x. Now 1 over 9, that's 1 over 3 squared. 1 over means I could write that as 3 to the negative second power, right? That's how you flip it in the denominator, make it positive. Beautiful. Good job, everybody. Now let's see, we got to use our laws of exponents to clean up. These get multiplied. These get multiplied. So I have 3 to the 4x times 3 to the 9 minus 3x equals 3 to the negative second. And then do you remember, what do we do with exponents now if we're multiplying two terms and they have the same base? Why, yes, we add them. So this would be 3 to the 4x plus 9 minus 3x equals 3 to the negative second. And then now we are home free. You see how both sides of the equations are 3 to the something? And exponential functions are 1 to 1. So if you have a to the x equals a to the y, that's an a. I don't know why I wrote it with no tail. There. Then that means x equals y. You can just set the exponents equal to each other and drop the base. Drop the base, please. Okay. So then we have 4x plus 9 minus 3x. That's just x plus 9 equals negative 2. So x is negative 11. Exponential equations have no restrictions. Their domains are all real numbers, and if you want to come back and check, you can, but there's no issue with negative 11 as a solution. It's not so high maintenance like a logarithmic equation. So that goes in the solution set. Okay. Last problem on the test. I always do 10 questions. 10 points a problem. Interest, exponential growth and decay. So find the amount owed at the end of 8 years if $5,000 is loaned at a rate of 5% compounded monthly. So we have to use compound interest formula. A equals P times 1 plus R divided by N raised to the NT. They want us to find the final amount owed. So we need to find A at the end of 8 years. So T is 8. The $5,000, that's the principal. That's the initial amount loaned. The rate of 5% would be 0.05 in our formula. Change that to a decimal. And compounded monthly means N is 12. N is the number of times that interest is compounded in 1 year. So that's everything. I do let them have a calculator, obviously. So this is going to be 5,000 times 1 plus 0.05 divided by 12 raised to the 12 times 8. And that's all I require them to show. From here, you know, they can just punch everything in their calculator. Since we're dealing with money, we round to the nearest cent. So 2 decimal places. 7452.93 is what you should get. Okay. And then last problem. Strontium-90 decays at a constant rate of 2.44% per year. Therefore, the equation for the amount P of strontium-90 after 10 years, or T years, excuse me, is P equals P naught E to the negative 0.0244 T. So I did take pity on their poor souls, and I just gave them the equation here. They didn't have to go find K. K, R, same thing, the decay rate. I just gave them the formula. How long will it take for 15 grams to decay to 5 grams? Round your answer to 2 decimal places. So 15 is the starting amount. That's P naught. Some people mess that up. P naught, we start with 15 and we're going to decay to 5, and we want to know how long that's going to take. So we're solving for T. Okay. That should have been the first step. Then from there, we're going to divide both sides by 15. So 5 divided by 15 equals e to the negative 0.0244t. That's 1/3. And you don't want to start writing 0.33 because you'll get some rounding error, okay? From here, the next step is you take the natural log of both sides. And natural log of e is just going to all cancel out. So on the right, I have negative 0.0244t equals ln 1/3. And then last step to get t, it's ln 1/3 divided by negative 0.0244. And then if you punch that in your calculator, it should be approximately 45.03 years. And that's it. So the last page, everybody got right. It was pretty straightforward. We did some spicier examples in class with half-life and stuff, but there was quite a bit of graphing and other important topics. I always do 2 chapters per exam for pre-calc. So they take 4 exams and a final. My calculus classes take only 3 exams and a final. There's less topics covered in calculus. They're more beefy, I would say, for sure. But pre-calc is hard because there's just so much material covered, right? Such an array of topics. It's really a review of all of your algebra, all of your trigonometry, everything you've ever learned in math in one semester. It blazes through to get you really primed up for calculus. That's why it's called pre-calculus. So I hope you enjoyed watching me solve this exam. I also will be solving the most recent Calc 2 exam. Calc 1 is going to take their test after spring break, so they haven't taken one yet. And then I don't have a Calc 3 class this semester, but if you guys want to see the second exam from last semester, I could solve that too. I know I've been neglecting you Calc 3 students. My apologies. Anyways, hope you enjoyed the video. Give it a thumbs up. Leave me a comment down below. If you're in Calc, how would you have done? I find that a lot of my calculus students forget a good amount of the pre-calc, and if they went back and were to take it, they would struggle. So I always tell the pre-calc kids, like, don't feel badly if you feel overwhelmed. This is normal. It is normal. That's pretty much it. Give the video a thumbs up. Subscribe if you haven't already. Check out all the video lectures on my playlist. You'll find them helpful. And you can also follow me on Instagram, TikTok, Twitter, Math with Professor V. You guys, I put up a little clip of me grading one of my Calc 1 students' exams. She gave me her permission, and it's going semi-viral on TikTok. So funny, just because she writes so beautifully. And she told me she didn't always have nice writing. She practiced it a few years ago because it upset her so much that she didn't have nice handwriting. So don't be one of those people who's like, I have bad handwriting. You can work on it, because I did that too. I remember my dad making fun of me when I was in like elementary school, saying how ugly I wrote. And I don't think any of you would say I write ugly now. So it can be done. Have some self-control and practice. All right, that's it. I'm done. I'm off to ballet. I'll talk to you guys later. Love you. Bye.